Imagine standing before a structure, not merely old, but ancient. A colossal edifice, erected 2 millennia ago, its very fabric still defiant against the relentless march of time, against the ravages of wind, rain, and the ceaseless assault of the elements. Now, contrast that with the concrete jungles of our modern world, where the lifespan of even the most robust structures is measured in decades, perhaps a century or two, before cracks spiderweb across their surfaces, before steel rebar rusts and expands, before the very material begins to crumble into dust. This stark difference is not a trick of the light, nor a testament to some forgotten magic, but rather a profound scientific mystery that has captivated engineers, archaeologists, and chemists for generations. We are speaking, of course, of ancient Roman concrete, a material so extraordinarily durable, so fundamentally advanced, that its secrets are only now, in the 21st century, beginning to yield to the patient probing of modern science. How did a civilization, without our sophisticated tools or chemical understanding, craft a building material that not only endures but, in some remarkable instances, appears to grow stronger with age, even capable of self-repair? The answer is a fascinating journey into the heart of Roman ingenuity, a tale of harnessing the raw power of the earth, and a humbling lesson for our own era of rapid decay. The story of Roman concrete, or opus caementitium as it was known, is not merely about a building material. It is about an empire's ambition made manifest. While rudimentary forms of lime mortar had existed for centuries in various cultures, the Romans elevated concrete to an art and a science, fundamentally transforming their architectural capabilities. Evidence suggests its early adoption began in the Republican era, perhaps as early as the 3rd or 2nd century BCE, but it was during the imperial period, from the 1st century BCE through the 4th century CE, that its use became ubiquitous and truly revolutionary. Before concrete, monumental structures were painstakingly assembled from massive, individually cut blocks of stone, a process requiring immense labor, precise craftsmanship, and considerable time. Imagine the sheer logistical challenge of quarrying, transporting, and hoisting colossal stones to construct a temple or an aqueduct. Roman concrete offered an alternative that was not only faster and more economical, but also allowed for unprecedented architectural freedom. Suddenly, architects were no longer constrained by the linear geometries of cut stone. Vaults, domes, and arches of immense scale and complexity became feasible, enabling the construction of spaces that were previously unimaginable. The Pantheon, with its majestic unreinforced concrete dome spanning over 43 meters, completed around 126 CE, stands as the crowning achievement of this material, its vast interior a testament to the Romans' mastery. The Colosseum, begun in 70 CE, while faced with marble and brick, relies fundamentally on a massive concrete core, providing its structural integrity. The sprawling baths of Caracalla, constructed between 212 and 217 CE, were a triumph of concrete engineering, encompassing vast vaulted halls that dwarfed any predecessors. At the heart of this innovation lay a deceptively simple recipe, recorded by ancient authors such as Vitruvius in his De Architectura and Pliny the Elder in his Natural History. The primary components were quicklime, water, and an aggregate of various materials like tuff, brick fragments, or local rock. But the secret ingredient, the true catalyst that set Roman concrete apart, was a peculiar type of volcanic ash known as pozzolana. This ash, named after Pozzuoli, a town near Naples in the volcanic Phlegrean fields, was not just any inert filler. It possessed extraordinary reactive properties. The Romans understood, perhaps through generations of empirical observation, that when this ash was mixed with lime and water, it created a material of unparalleled strength and endurance. The geological bounty of the Italian peninsula, particularly its volcanic regions, provided the Romans with an abundant supply of this crucial ingredient. Pozzolana was quarried from areas like Monte Cavo near Rome, or even further south in the shadow of Mount Vesuvius. The ash, rich in silica and alumina, was a gift from the very earth that nourished their empire. When combined, these ingredients formed a composite material that could be poured into wooden molds, allowing for rapid construction and complex forms. This ability to cast structures rather than carve them transformed the very nature of Roman building. From the mighty aqueducts that channeled water across vast distances, like the Pont du Gard built around 19 BCE, to the robust foundations of roads and bridges, and crucially, to the intricate marine structures like the breakwaters of Portus near Ostia and the harbor at Caesarea Maritima, Roman concrete was the silent, enduring backbone of an empire that spanned continents. These marine structures, in particular, present some of the most compelling evidence of Roman concrete's extraordinary durability, often surviving submerged in corrosive seawater for 2 millennia, where modern equivalents would succumb in mere decades. The true marvel of Roman concrete, however, lies not just in its ingredients, but in the intricate chemical reactions that unfold over centuries, reactions that defy our conventional understanding of construction materials. Modern Portland cement concrete, the backbone of contemporary construction, achieves its strength through the formation of calcium silicate hydrate, or CSH, when cement reacts with water. This process is relatively fast, and while effective, the resulting CSH phases are susceptible to degradation over time, particularly from the ingress of water, chlorides, and sulfates, leading to cracking, spalling, and eventual structural failure. Roman concrete operates on an entirely different principle, one rooted in the unique properties of pozzolana. When the volcanic ash, rich in amorphous silica and alumina, is mixed with lime, calcium oxide, and water, a complex chemical dance begins. This is known as a pozzolanic reaction. Instead of forming just CSH, Roman concrete forms denser, more stable calcium aluminum silicate hydrate, or CSH. This CSH is a fundamentally different mineralogical structure, providing superior long-term stability and resistance to chemical attack. But the story deepens, particularly with the marine concrete used in Roman harbors and breakwaters. For centuries, it was observed that these submerged structures not only resisted the corrosive power of seawater, but actually appeared to thrive in it. Modern scientific investigations, spearheaded by researchers such as Professor Marie Jackson at the University of Utah, have finally begun to unravel this profound mystery. Utilizing advanced techniques like scanning electron microscopy, X-ray diffraction, and microcomputed tomography on core samples retrieved from ancient Roman marine structures, scientists have identified a crucial additional component: the formation of secondary mineral phases. When seawater infiltrates microcracks in the Roman concrete, it interacts with the lime and volcanic ash that haven't fully reacted. This ongoing chemical process, fueled by the minerals present in seawater, especially magnesium, potassium, and sulfates, leads to the slow crystallization of new, highly stable minerals. Chief among these are strathlingite and philipsite, along with a particularly robust form of strontium aluminate silicate hydrate, or SiSH. These minerals are not merely inert fillers. They are strong, interlocking crystals that grow within the concrete matrix, effectively healing microcracks as they form. This means that Roman concrete, especially when exposed to water, possesses an extraordinary capacity for self-repair. Think of it. As modern concrete begins its slow, inevitable decline from the moment it is poured, Roman concrete, particularly in its marine application, is a living material, constantly evolving and strengthening itself. The very elements that would hasten the decay of contemporary structures, water, salts, temperature fluctuations, become catalysts for the Roman material's longevity. Seawater, with its dissolved chlorides and sulfates, which notoriously attack and corrode the steel reinforcement in modern concrete and cause it to spall, instead provides the raw materials for Roman concrete to grow new, stable mineral phases. It's a counterintuitive triumph of material science, a system where the environment, rather than being a destructive force, becomes an active participant in the material's preservation and enhancement. The specific combination of volcanic ash from the Phlegrean fields, which contains unique mineralogical properties, and the precise ratios of lime, along with the subsequent interaction with water over millennia, creates a kind of geological alchemy. The low heat of hydration during the initial setting phase, compared to modern Portland cement, also contributed to fewer thermal cracks, allowing the self-healing process to be more effective over time. This slow, deliberate curing process, coupled with the unique mineralogical composition, produced a concrete that became denser, more impermeable, and structurally more resilient with each passing century. It is a material that literally improves with age, transforming from a simple mixture of earth and water into a crystalline fortress, a testament to an ancient wisdom that understood how to cooperate with natural processes rather than trying to overpower them. The profound irony of Roman concrete's story is that this advanced material science, this knowledge of how to craft structures that could defy millennia, was largely forgotten for over 1,300 years. With the decline and eventual fall of the Western Roman Empire in 476 CE, the intricate knowledge, the specific sourcing of materials, and the specialized construction techniques gradually faded into obscurity. Europe entered a period where building methods reverted to simpler, less sophisticated techniques, predominantly relying on cut stone and timber. The monumental scale and complex forms enabled by Roman concrete became architectural memories, marvels of a bygone era, their construction methods an enigma. It wasn't until the late 18th and early 19th centuries that concrete, in a new form, began its resurgence. This revival culminated in the invention of Portland cement in 1824 by Joseph Aspdin, an English bricklayer. Modern Portland cement, made by heating limestone and clay to very high temperatures, then grinding the resulting clinker, became the foundation of our contemporary built environment. It allowed for rapid construction on an unprecedented scale, underpinning the Industrial Revolution and shaping the skylines of every major city. Yet, the concrete we use today, while revolutionary in its own right, carries a fundamental flaw when compared to its ancient predecessor: it degrades. Modern concrete structures, even those built to the highest standards, typically have a design life of 50 to 100 years. They are vulnerable to a host of environmental stressors. Freeze-thaw cycles cause expansion and contraction, leading to cracks. Carbonation, where atmospheric carbon dioxide reacts with the cement, reduces its alkalinity and leaves steel reinforcement vulnerable to corrosion. The ingress of chlorides from road salt or seawater accelerates this corrosion, causing the steel to expand, which in turn cracks the concrete from within, a process known as spalling. Sulfates in groundwater or seawater can react with the cement paste, leading to expansion and disintegration. Our modern marvels require constant maintenance, costly repairs, and ultimately, replacement. The Pantheon, at nearly 1,900 years old, has stood with minimal intervention, while many 20th century concrete structures are already facing demolition or extensive restoration. This stark contrast presents the twist in our narrative. We believed we had advanced, but in some crucial respects, we had forgotten a superior technology. The Roman engineers, through empirical knowledge passed down and perfected, had stumbled upon a method that was not merely durable but, fundamentally, sustainable in a way modern concrete is not. The production of Portland cement is an energy-intensive process responsible for an estimated 8% of global carbon dioxide emissions. The short lifespan of modern concrete means a continuous cycle of demolition and reconstruction, each cycle contributing to environmental impact. The rediscovery of Roman concrete secrets is not just an academic curiosity. It holds profound implications for our future. In recent decades, a dedicated cadre of material scientists, archaeologists, and engineers have turned their attention to these ancient ruins, not merely to admire them, but to understand them. Researchers like Marie Jackson, building on the work of others, have painstakingly analyzed core samples, employing cutting-edge analytical tools to peer into the atomic structure of these millennia-old materials. Their findings, particularly the identification of the self-healing mechanisms and the stable mineral phases like SASH and stratlingite, have opened a new frontier in materials science. The challenge now is to translate this ancient wisdom into modern application. Can we recreate Roman concrete, or adapt its principles, to build more resilient, longer-lasting, and environmentally friendly infrastructure? The exact volcanic ash used by the Romans from Pozzuoli is a specific geological formation not universally available. However, scientists are exploring other pozzolanic materials, including fly ash from coal combustion and metakaolin, which could emulate the Roman recipe's performance. There are ongoing projects to develop self-healing concretes that incorporate polymers or bacteria, but the Roman method offers a purely mineralogical solution, leveraging natural geological processes. Imagine a future where marine barriers, seawalls, and even nuclear waste repositories could be constructed from materials that strengthen themselves over centuries, impervious to the very forces that degrade our current structures. Imagine reducing the colossal carbon footprint of cement production and the waste generated by frequent demolition. The lessons from Roman concrete extend beyond mere durability. They speak to a philosophy of building in harmony with nature, of creating materials that engage with their environment rather than resisting it until failure. The enduring legacy of Roman concrete is not just in the magnificent ruins that the Mediterranean landscape, but in the compelling questions it poses to our contemporary world. It challenges our assumptions about progress, reminds us that true innovation can sometimes be found in forgotten wisdom, and offers a tantalizing glimpse into a future where our built environment is not locked in a losing battle against time and the elements, but rather evolves, strengthens, and endures, just as the Roman Empire once sought to do. The silent strength of the Pantheon, the submerged resilience of ancient harbors, they are not just monuments to a past empire, but living laboratories, whispering secrets of lasting construction across the vast chasm of history, secrets we are finally beginning to hear and understand.